This part of the presentation will illustrate drawing basic timing diagrams in TimingDesigner. We will cover clocks, signals, and buses, followed by edge events, which will include delays and constraints. And lastly, we will go over edge events and the parameter spreadsheet, where we will look at variables, functions, and an example diagram of a Shark DSP processor. So let's see what's involved in drawing simple diagrams by implementing a simple protocol. We'll create a diagram that should look like this one when we're finished. This is a write operation for some device. Here we need a clock, a chip enable, an address bus, a write enable, and a data bus. We'll start by drawing a clock. By selecting the clock toolbar button, the clock attribute dialog box will be presented allowing definition of a clock name, any descriptive comments associated with it, and a frequency or period. We can also define a duty cycle with a default set at 50%, an offset increment to place the first rising edge of the clock at an appropriate distance from the left margin, and separately specify rising and falling edge jitter. For our example, we'll use CLK as the name, specify a clock frequency of 50 MHz, and a jitter of 1 nanosecond for both rising and falling edges. The clock is automatically drawn once the dialog box is completed by selecting the OK button. Just a note about naming waveforms. TimingDesigner allows just about any character string for a waveform name. However, it's strongly recommended that legal HDL waveform names be used so that any future reference of a waveform from a derived signal will respond correctly. TimingDesigner supports Verilog or VHDL syntax for derived signals, so any reference of an existing waveform in a derived signal equation must be syntactically correct in order for the derived signal to be evaluated properly. Derived signals and clocks will be covered later. Next, we'll draw our control signals for the protocol using the signal waveform tool for the chip enable and write enable. Selecting the signal toolbar button, we're presented with the signal attribute dialog box allowing a name, a descriptive comment, and an initial state. Drawing the chip enable signal first, we enter the signal name and select the low initial state. Selecting the OK button will place the signal in the diagram ready for edge transition placements. Simply point and click the area where you wish to place an edge state transition, and TimingDesigner will automatically draw the signal to that point, toggling between a high and low state with each mouse click. You can easily change the next toggle state by selecting the desired next state button before placing the next edge. The last two successive state values used for the signal will be current toggle states. The end marker is a termination point for the diagram, so any click to its right will terminate that particular waveform. We can repeat this procedure for drawing the write enable signal, but since these two signals are similar in characteristics for this protocol, let's just copy it. Select the waveform number at the left margin and select Edit Copy or Control-C from the keyboard to copy the waveform. Then select Edit Paste or Control-V from the keyboard to paste the copied signal at the bottom of the diagram. You can copy any waveform in the diagram in this fashion. The copied signal will be named similarly, appended with a numeric increment to avoid identical signal names. We can either double-click the waveform name or bring up the attribute dialog box to rename the signal appropriately. We now need to add an intermediate state in the write enable signal. State changes can be added to completed signals using the pulse tool. Once selected, any click in a waveform state will insert a pulse event to the waveform for high, low, or high Z signal states, and a single state change for valid or invalid states. To exit this pulse tool, select the pointer tool from either the left toolbar button or a right mouse click. We'll just move the edges apart here by dragging them out a bit with the mouse. Now let's draw our address and data buses. With TimingDesigner, you can draw a bus using a signal waveform, but we recommend using the bus waveform, which allows easy expansion and collapse of a bus into its associated bus elements. There are two bus types supported, virtual and derived. We'll cover virtual buses first. Selecting the bus waveform tool, we again are presented with the tool's attribute dialog box. By default, the bus is set up as a virtual bus, which is essentially what you would normally expect the bus waveform to look like, simply a signal with valid states and no definitive size declaration. Virtual buses only allow valid, invalid, and tri-state signal states. Let's draw the address bus first. So enter the name, optional comment, and set an initial state in the bus attribute dialog box. We'll set it as invalid. Selecting the OK button will place the bus in a diagram so that you can now draw its characteristics. Place the edge transitions where desired with mouse clicks, change the toggle sequence if desired, and then terminate the bus with a click outside of the end marker. Next, we'll add bus values to the valid states. A double click on the desired edge state will present the edge state attribute dialog box, where all information associated with the edge state is contained. In the appearance area, we notice the default selection of value is selected with an active value field. Here, we enter a 5 for the bus value. Selecting the advance arrow in the lower right corner will advance to the next state, where we again enter a value for the valid state of 3. Once all the valid states have values set, we can then select OK to close the edge state attribute dialog box. Now that we have assigned distinct values to our virtual bus, we can expand it into its individual elements by converting it to a derived bus. Open the bus attribute dialog box by double-clicking on the bus waveform number, then select a derived type, and assign the bus size by entering a value for the most significant bit and least significant bit fields. Selecting OK will now expand the bus into its now defined individual elements. Notice that the individual signal names are appended with the appropriate bit it represents, and all the state values are represented at the bit level. Also notice the virtual representation of the bus is still presented as a reference waveform. All edits to the bus must now be done on the element waveform positions, which will have their characteristics continually reflected in the virtual representation of the bus waveform. To collapse the bus back to a virtual bus, simply repeat the conversion process, selecting Virtual. This feature is extremely useful for creating large bus structures where each individual element needs to be drawn in some fashion without having to go through the exercise of drawing each bus element individually. To draw a data bus, we can simply repeat previously described steps for drawing the address bus.